Okay, good morning, everybody. So let's start. Today we have the pleasure of welcoming Sonia and Hedri. So Sonia did her PhD in Stanford in SLAC on dark matter phenomenology. Then she continued with postdocs in Gutenberg University in Mainz and Nijmegen in Amsterdam, still working on dark matter phenomenology. So she comes from particle astrophysics. And then she came back to France to do a postdoc in Laboratoire Le Prince Ringuet in Palaiseau. And then she switched to working on neutrino astrophysics, the field in which she continues to working now. And in 2021, she was recruited as a CNRS researcher in APC, so not far from here. She's a member of the Antares and KM3Net collaborations, and she's working on neutrino astrophysics and specifically astrophysical sources of neutrinos, for example, core collapse supernova, on which she's going to talk today. So thank you, Sonia.
Thank you, Irina. Is the microphone working? Perfect. So thank you everyone for joining and good morning. As Irina has said, I'm going to talk to you about how to get straight to the core of a collapsing star using neutrinos, about why it's quite difficult and why you should do it anyway. So a core collapse supernova, is a slide not working? Of course, it has to. A core collapse supernova is what happens at the end of life of a massive star, of a heavy star, more than 8 solar masses, after it has gone through its main sequence nuclear fusion steps, as well as all the nuclear fusion steps of hydrogen into helium, as well as all the subsequent steps involving heavier and heavier elements, down, all the way down to iron. So at this point of its life, the dynamics of the star is quite difficult to probe directly because the radius of the star itself can reach up to hundreds of million kilometers, while most of the action happens in this core, which is, as you can see, the size of a planet. However, we can infer what happens in the core of the star based on the laws of physics. In particular, we can infer that after we have reached iron, nuclear fusion cannot counter gravitational collapse anymore. In lighter stars, gravitational collapse can still be countered by the Fermi pressure of electrons in the core of the star. However, beyond this 8 solar mass threshold, this Fermi pressure is reduced by the fact that electrons get captured on protons. At this point, nothing hinders the collapse of the core of the star under gravitational forces, and you get a supernova. The supernova itself is a rapid succession of extremely complex phenomena taking a fraction of a second total. So as I said, it's extremely difficult to observe. However, we can understand what happens during a supernova through simulations. And in particular, a robust prediction of simulations is that a supernova occurs in 3 steps. The first step is the formation of what we call a protoneutron star due to collapsing matter. That is an extremely dense region inside the core where nucleons are packed against each other, a density 10 to the 12 grams per centimeter cubed. This region is so dense that the rest of the collapsing matter is going to bounce on it, leading to the formation of a shock wave which propagates outwards. This is the official beginning of the supernova. This phase lasts a few tenths of milliseconds. At that point, you might think, okay, the star is just going to explode. But actually, in most simulations, the shock wave is going to stall deep inside the core, like this. And the star enters in what is called the accretion phase, where matter continues collapsing onto the protoneutron star, passing through the shock wave. While matter is passing through the shock wave, nuclei get dissociated into 3 nucleons. So around the protoneutron star, you have this extremely hot mantle with a temperature of 100 billion degrees and 3 nucleons flying around. This is what we call in scientific terms a gigantic mess. So what is going to happen in this gigantic mess is going to determine whether the star undergoes a complete collapse into a black hole, or whether somehow the shock wave restarts and you get an explosion which leaves behind a neutron star. Notice the somehow here, because in fact, the behavior of this mantle is so complex that in current supernova simulations, it is extremely hard to get an explosion. And most of the time, the explosions you are going to get are not as powerful as what is actually being observed in the cosmos. As I mentioned, observing directly the core of the star using photons is not possible. But, and here you see what I'm coming at, during a supernova, you expect the emission of a short but also extremely intense burst of neutrinos. These neutrinos are expected to play a key role in the explosion by depositing a small fraction, a few percent of their energy, below the shock wave, creating a kind of a pressure cooker effect. In addition to playing a key role in the explosion, neutrino rates and energy spectra could give you a complete recording of what is happening in the core of the star during the supernova. To understand this, let's retrace the different steps I exposed earlier, but from the point of view of neutrino production. Well, the idea is that the core of the star is too dense for the shock wave to be able to lift all the upper layers of the star. This is a matter of, this is a problem of mechanics. Like the star is pushing, like it's trying to counter the gravitational collapse and it's not succeeding at it. So you need to find an additional source of energy to power this shock wave. And this is a combination of complex factors like neutrino energy deposition and hydrodynamical instabilities that could concentrate the energy in one point, for example. But in general, you don't have one factor, you have several of them. So let's start for neutrino production. Let's start with the initial shock propagation. When it starts propagating, the shock wave is going to dissociate nuclei into free nucleons. In particular, you're going to have free protons, which will capture the electrons that are flying around. This leads to the production of an intense burst of electron neutrinos with this very characteristic peak. Then during the accretion phase, you have a similar captured phenomenon, but this time this capture is going to involve both electrons and positrons because of this pair production mechanism due to photon conversion in the hot mantle. So now you are going to have production dominantly of electron neutrinos and electron antineutrinos. And as you see, this production has a very complex profile. If you look at the luminosity of neutrinos, it's correlated with the accretion rate of matter onto the core. And you have these oscillatory profiles with oscillations which correspond to hydrodynamical instabilities. I can tell you more about it later. And then you start having these other neutrino flavors like muon and tau that we write using an X here. And they come from the deepest regions of the star, which are cooling down through neutral current interactions. You have a nucleon here producing pairs of neutrinos and antineutrinos of all flavors. This equal production of all flavors through cooling can be seen after an explosion, when all is left behind is a neutron star. And you have this exponentially decreasing profile. So the scale here is not the same. So as you can see, we have gone from having this photon information from the explosion, which is extremely indirect, to having a direct record and complete recording of the core of the star with millisecond precision on free channels corresponding to these free neutrino species. This is extremely informative. So how many times did we actually make this observation? The answer is once, and I'm not going to tell you how many years ago because this was my year of birth. So in 1987, a star exploded in the Large Magellanic Cloud around 50 kiloparsec away from us. You can see the explosion here, invisible light. And this explosion was associated with the observation of 25 neutrinos in free experiments, Kamiokande-2, IMB, and Baksan. But 25 neutrinos in free experiments is really not a lot, but from their energy and time profiles, we can already learn a few important things about the behavior of the star. For example, you see that this time profile extends up to around 10 or 11 seconds, which is consistent with the existence of a cooling phase. And here you have this higher concentration of neutrinos consistent with the existence of this accretion phase. So here we demonstrate that there are indeed supernovae for which the shock wave is stalling inside the core. In addition, looking at the energies, neutrinos are thermal and their tens of MeV energies reflect the temperature of the star's core. In addition to this interesting physics, SN 1987A gives us a few lessons on how to observe the next galactic supernova using neutrinos. The first lesson is that current and upcoming neutrino experiments will be mainly sensitive to supernovae occurring in our immediate neighborhood, our galaxy or the Large Magellanic Cloud. And these supernovae are expected to occur only 2 or 3 times per century. In addition to being extremely rare, this phenomenon is extremely hard to predict. And this can have quite scary consequences. For example, here on the right, you can see an event record of neutrinos at Kamiokande 2 around the time of SN 1987A. This event record has the peak here, the Nobel Prize winning peak, but it also has a gap here that occurred around 2 minutes before this peak, this gap corresponding to a scheduled detector maintenance. And the fact that this maintenance did not occur at the time the neutrinos arrived is pure luck. We had no way to know. So the lesson here is that the best experiment to observe supernova neutrinos is not the one that is the biggest, it's not the one that has the highest resolution, it's the one that is actually working when your supernova neutrinos are arriving. From this observation, we can infer the current supernova observation strategy, which rests on 2 requirements. The first requirement is to involve as many experiments as possible, even experiments that have not been made initially to detect supernova neutrinos, and even experiments that have not been made initially to detect neutrinos at all, like, for example, dark matter experiments. In addition to this requirement, we also require that these experiments communicate with each other in real time, analyze their data as fast as possible, and communicate their findings to telescopes. And I'm going to expand on this requirement more during this presentation. This is why right now we're having experiments all over the world having this supernova neutrino detection program. I'm only showing a few examples here. And these experiments are sending their data in real time to what we call the Supernova Early Warning System, which is a centralized neutrino data analysis network. You can see the website here. We call it SNEWS. So during this presentation, I'm going to illustrate a bit these 2 aspects of the supernova neutrino observation strategy by presenting how to detect supernova neutrinos in an experiment that was not initially designed for it, the KM3net neutrino detector, and by showing you how and why to pool together the data from several different neutrino experiments, including next generation experiments. Let me start with the detection of supernova neutrinos in the KM3net experiment. KM3net is a neutrino detector, an extremely large-scale neutrino detector located in the Mediterranean Sea. Why the Mediterranean Sea? Because KM3net is looking for this blue Cherenkov of light emitted by relativistic charged particles traveling in water, including, above all, neutrino interaction products. This light is detected by these photomultipliers, which are arranged in spherical structure called digital optical modules, the DOM. I'm going to talk a lot about it, so I'm going to use this acronym a lot. These DOMs are arranged along these lines, these strings here, and the lines are put together to form a gigantic detection array. And here on the right, you can see a video of an animation of what is happening to this array. Like you have a charged particle passing by and the photomultipliers being activated as they receive the light. This structure has 2 important advantages. First, it is highly modular. It means that you can start taking data even when your detector is not finished. You can have a few lines installed somewhere and then install a few other ones while you are taking data. And the second advantage is that just by varying the spacing between the optical modules, you can be sensitive to different energy ranges. In practice, KM3net exploits this fact by having 2 different detectors, 2 different arrays, ORCA off the Toulon coast and ARCA near Sicily. Here you see a schematic vision to scale of what the ARCA and ORCA arrays are going to look like. What is important to know here is that each of these blocks here, called binding blocks, has the same number of optical modules. So what is changing between this one and this one is the spacing. ORCA is, well, as you can see, the densest detector. It's sensitive to what we call low energy, which is like GeV scale neutrinos from produced in the atmosphere, and it's for oscillation studies. ARCA is the least dense array. It's targeting much higher energies, and it's aimed at the detection of astrophysical neutrinos. A final building block is going to be 115 lines in hopefully 2027. Right now, about 12% of the detector is in place, 28 lines in ARCA, 18 lines in ORCA. And periodically, as you can see in the video above, we are going out with a boat. I mean, we colleagues are going out with a boat, and they are loading new lines. So here is a picture of the line being loaded. Since a line can be very long, it can be 1 kilometer long, it's rolled up inside this sphere. If you look, you can see the optical modules here. So this sphere is anchored to the ground with this yellow structure where you do all the branching, cabling, etc. And it's lowered to the seafloor using a crane. And on the seafloor, there is a robot which plugs in everything and unfurls the sphere. So we take the scaffolding back and the line is just floating. So ChemFreeNet is an impressive structure, but it has one problem for supernova neutrino detection, which is that its lower energy threshold is still several orders of magnitude higher than the tens of MeV of supernova neutrinos. So to try to detect supernova neutrinos at ChemFreeNet, we have to go off the beaten path. So first, let's consider let's notice that the dominant neutrino interaction mode for these energies is the inverse beta decay of electron antineutrinos and protons. So who says supernova detection with water Cherenkov detectors says electron antineutrinos. This inverse beta decay produces, among other things, a positron, which emits Cherenkov light. First, good news. The difficulty here is that at these energies, the amount of Cherenkov light emitted will be so localized that in a best case scenario, it will activate a single digital optical module. So at the scale of ChemFreeNet, at zeroth order, what we get is a single blip without reconstruction being possible. This is not necessarily a problem because the supernova signal is expected to be concentrated in time, around half a second, and it's expected to be extremely intense. So what we could see is a rise of the number of activated optical modules above the ambient noise. And this rise and the shape of this rise can be extremely informative already. You can learn about the start of the supernova, its outcome, the existence of hydrodynamical instabilities, and the rate of the collapse, for example. However, whether or not you are going to get this information depends on the level and stability of this noise down there. And the difficulty here is that we are in a natural environment that is extremely difficult to control. Also, it is darker and less lively than here. So when faced with an extremely difficult question like this, I tried to be modern and first asked ChatGPT what it was thinking about supernova neutrino detection in the Mediterranean Sea. And I must say it gave me quite creative answers. First, it noticed that the Mediterranean Sea is located near several regions of the sky that are expected to contain many supernova explosions. So bring sunscreen, I guess. However, while the Mediterranean Sea is a large body of water, it does not have the detectors needed to detect supernova neutrinos, so too bad. And additionally, it's hard to detect neutrinos there because the sea is not located underground. Also, I think being located underwater is pretty nice. So AI has declared defeat, and I went back to science, which told me that at the energies of supernova neutrinos, there are two main types of backgrounds. Radioactivity, mainly from potassium-40 decays in seawater, and light from living organisms. So these two backgrounds total 200 kilohertz noise per optical module. This is huge. And the bioluminescence background is unstable. So here you can see an event record at the Antares experiment, which is the precursor of ChemFreeNet, which saw these short bursts on timescales which are relatively similar to the supernova neutrino emission timescales. However, well, even with the stable components that you can see on this plot, when ORCA and ARCA will be finished, we expect to see 600 million background events in a supernova analysis time window. So that is what nature brings you, I guess. So here we'll have to be a bit more subtle. We'll have to do a bit of reconstruction after all. And to do reconstruction, we are going to exploit the fact that a ChemFreeNet optical module is actually made of 31 3-inch photomultipliers. Since these photomultipliers are close to each other within a sphere of 44 centimeter diameter, It is definitely possible for the Cherenkov light of supernova neutrino interaction products to activate several photomultipliers. So instead of having a single blip that you cannot reconstruct, you have a pattern which you can analyze. And the simplest thing you can actually do is to count the number of photomultiplier hits within a time window of a few tenths of nanosecond to ensure that they all come from the same particle. So this is an observable we call the multiplicity. And this multiplicity is plotted here. Multiplicity distribution is plotted here. For data, as you can see the black points. I'm sorry, I have lost my mouse. And for background simulations. The first good news is that for the backgrounds that we have been worried about, bioluminescence and radioactivity, are mainly concentrated at the single hit level. When we increase the multiplicity, when we go higher like this, radioactivity backgrounds fall extremely sharply. This fall is mitigated by the fact that at some point you run into backgrounds from muons produced by cosmic ray interactions in the atmosphere. However, these muons are high energy in general, so they leave very obvious signatures in the detector. You can see it on the right here with each ball representing a digital optical module. They leave these tracks, and these tracks are most of the times well identified by chem-freenet triggers, high energy triggers. These findings form the two main ingredients of the published current supernova analysis at chem-freenet. This analysis rests mainly on the existence of a muon veto, where we remove the optical modules associated with chem-freenet triggers in time and space, and on a selection on this multiplicity observable. Here we define it as a number of hits in a 10 nanosecond window, so we narrowed it a bit compared to what I explained before. You can see here on the right background and signal distributions of this multiplicity in a final chem-freenet building block of 115 lines. So here we have a 0.5 second analysis window. The light blue triangles show what you expect as a background in ORCA. The dark blue triangles are what you expect in ARCA. And then the field histograms are for 3 different signals with 3 different progenitor masses in units of solar masses. This is at 10 kiloparsec away from us. So here you can see there is a definite sweet spot. And we can characterize this sweet spot by maximizing the detection horizon of chem-freenet. And we find that this sweet spot is a region with multiplicities 7 to 11. What is the sensitivity associated with this muon veto plus multiplicity selection? Well, here this plot shows the multiplicity as a function of the distance to us in kiloparsec, supernova distance to us, the sensitivity as a function of the distance, for the 3 different models. So the green one, the 11 solar mass, represents a quite pessimistic model, but also quite realistic since light progenitors are more frequent. The gray one with 27 solar masses represents quite an optimistic model. And the pink one represents an extreme model where you have an extremely heavy progenitor and black hole production. You see that for extreme models, we can reach up to the Large Magellanic Cloud. And in all, when we integrate over a prior on the supernova distance and a prior on the progenitor mass, we get 5 sigma sensitivity to 96% of potential galactic supernovae. So here, chem-freenet can definitely be an actor in the hunting for the next galactic supernova. However, there is a bit of room for improvements. Not only to turn this 96% into 100%, not only to gain sensitivity in the Large Magellanic Cloud, but also in order to improve our current sensitivity, because there is only 12% of the detector in place, and a supernova could occur tomorrow for what we know. So to improve this search, there is one clear path forward, which is to go beyond merely counting photomultiplier hits, and instead analyzing the shape of this pattern or its position, for example. So here, this was a work initiated by Gwenaëlle de Vassège at APC, who is now at UC Louvain. And I took it over working with Isabelle Goss and Miriam Bendaman, who is now in Naples. What we did is that we sat down and we started writing as many observables as possible that could help us characterize the pattern of activated photomultipliers. So in practice, we obtained 20 observables, which could be classified into 4 categories. One of them is how intense the overall signal is. The second one is the position, mean position of the heat cluster on the optical module. Third one is the spatial extension of your heat cluster. And fourth one is the time extension, how spread out it is in time. And then we use boosted decision trees to both select a minimal set of best observables and maximize the signal or background ratio. So both observable selection and signal and classification. With this boosted decision tree, we are able to prove that a full description of low energy signatures at ChemFreeNet could be made with 5 observables. 2 of them are related to the intensity of the signal. This is our multiplicity and the total charge deposited. And then the 3 others are in the one in each of the remaining categories. So we have 1 variable for the heat cluster concentration, spatial concentration, 1 variable for its height on the optical module, and another variable for the average time spread of the heats. And these 5 observables are enough. So to show you how they are working and why they are working, on the right, you can see the distribution of the height of the heat cluster and of the overall heat concentration for ChemFreeNet data taken like a few years earlier. And here to show the role of observables other than the multiplicity, I have fixed the multiplicity to be 7. So we have quite a complex pattern, a 7-pixel image to analyze. And here you see that this distribution is definitely bimodal. On one end of the distribution, you have radioactivity. Radioactivity is very low energy signal, so only vertices close to the optical module are going to be detected, which means that we are going to get the beginning of the Cherenkov cone, so a very concentrated signature. In addition, the bottom of the optical module is more instrumented. You can see the cap on the top that is obscuring the view. So there is going to be a strong preference for this bottom part. And additionally, you are going to have low charge deposited and very few hits. Muons have completely opposite properties. They are coming from above, so they are going to leave primarily deposits on the upper hemisphere of the optical module, and they have long trajectories, so they will deposit a high amount of light, and their signal is going to be spread out both in space and time. And the advantage of having these opposite properties is that in the middle, you have a sweet spot. And the signal fits right into it because it looks like radioactivity. Its topology is similar to radioactivity, but its energy is higher. So it's going to be less concentrated and it can creep into the upper part of the optical module. This is why these observables are working. We formalized this kind of qualitative observations by incorporating these 5 observables into a boosted decision tree. In fact, we had 1 boosted decision tree for each multiplicity. We trained it on a simulation for the signal, a giant force simulation, and on data for background. This led to systematics that we dealt with accordingly. You can see here that a test of this boosted decision tree in an upcoming configuration of our detectors with 29 lines for ARCA and 24 lines for ORCA. I say upcoming, it was supposed to be there for ICRC 2023, but we had a few delays. So here you can see the ORCA and ARCA backgrounds, and this blue histogram represents the total background you expect. And then you have our 3 supernova progenitors for a signal at the galactic center. So currently at ChemFreeNet, we are able to see any supernova, potential supernova at the galactic center. To have a more global view, we also plotted the sensitivity as a function of the distance for this upcoming ARCA and ORCA configuration. Here, the dashed lines are when we use the multiplicity only, so the old analysis. And the solid line is what we get when we introduce our boosted decision trees. In practice, we have a 23% increase of the distance horizon at ChemFreeNet with our new method. What it means is that for the most pessimistic, but also the most realistic model, the amount of stars in the galaxy of potential supernova progenitors we are going to probe goes from 33% to 52%. So this is actually quite a considerable improvement. And ChemFreeNet, with this new analysis, will be able to even now probe, or even in a few months, probe the majority of potential core collapse supernovae in the galaxy. Okay, so now we have shown that ChemFreeNet, even now, or even like next year, could probe most of supernovae in the galaxy and could be an actor in the hunt for the next galactic core collapse supernova. So of course, we are going to want to brag about it as fast as possible. So this is not quite the reason, I will explain it more later, but indeed the cuts that I have presented there are incorporated into a real-time analysis system that is processing ARCA and ORCA data and sending alerts within 20 seconds of the data reception to the Supernova Early Warning System, SNEWS. So the supernova selection that I have presented there is in this blue part there. We count the number of optical modules passing a certain threshold, like a selection threshold that I presented earlier. And if this number of optical modules is beyond the expected background, and if the p-value is small enough, we issue an alert. Of course, we can also receive alerts from SNEWS and dig into our database to see if we have anything interesting. And another part that is extremely important for supernova analysis is the buffering part. The idea here is that each time we issue a supernova alert, we also save 10 minutes of data around the time of this alert with extremely loose cuts. So you can see here what the time distribution of this data would look like in the final configuration of ARCA for a supernova at 5 kiloparsec. This is extremely noisy, but we could be able to track the evolution of the supernova neutrino rates as a function of time. Now, why tracking this evolution is important? Here, I think I made my point. I explained why we want to use neutrinos to dissect core collapse supernovae. But still, why do we want to make this dissection in real time, and why do we want to share it with the public? So this is not only a matter of ego, in fact. This is also because inside a star, neutrinos are going to travel considerably faster than the shock wave causing the explosion. For this reason, on Earth, we expect to see the supernova neutrinos several minutes to several hours before we actually see the explosion in optical, X-ray, infrared telescopes. And this delay depends only on the size of the star. So what this delay would allow us to do would be to use neutrinos to actually locate the supernova and send the relevant information to telescopes so that they can get as prompt information as prompt as possible about the explosion. So one first step in locating a supernova is finding its angular position in the sky. This can be done by estimating the supernova detection time at several experiments. So for example, you can take the rate curve, like the noisy rate curve that I presented 2 slides ago. You can smooth it out and fit it to have an estimation of the supernova detection time at KM3net. With the final ARCA configuration, you will get an 8 millisecond uncertainty for a supernova at the galactic center. With detectors that have less noise, that are more sensitive to core collapse supernovae, you could go down to a millisecond resolution. Such a precise resolution would allow us to compare the detection times of supernova neutrinos at different experiments located at different locations on Earth and locate the supernova in the sky using triangulation. There are other ways to locate a supernova. In some experiments, you can measure the neutrino direction, but triangulation has the advantage of involving any type of experiment. It's the location that matters, and of being extremely fast. So in 2020, there has been a study by Colero et al. About how precise triangulation could be. So here they try to shift the rising parts of the supernova rate curves between different experiments and see when they matched. And they performed a global study involving next generation experiments, such that the full configuration of KM3net ARCA, IceCube Generation 2, Juno, and Hyper-Kamiokande. And here on the right, you see some examples of the 90% confidence region in the sky for supernova localization. They showed that this 90% confidence region could be shrunk down to 140 degrees squared. And here this result will be obtained within minutes after detection. Now, what does 140 degrees squared mean for telescopes? Here I have shown the field of view of different telescopes associated with their optical depths in magnitude. And you can see that the field of view of the telescope varies a lot, and that the narrower the field of view, the deeper the telescope is. So in fact, the optimization of the telescope observation strategy will depend not only on the angular position of the supernova in the sky, it will also depend on where it's located actually in the galaxy, how far it is away from us. For example, here you can see a map of the optical magnitude of the supernova as a function of the position in the galaxy. The center of this map is the galactic center. On the left, you can see the Earth in this dark blue region. And you see that near the galactic center, the expected visibility of the supernova varies like by orders of magnitude over distances of a few kiloparsec. So all in all, angular position is not enough. We need the supernova distance. Who says measuring the distance of an astrophysical object means finding a standard candle. That is an observable whose initial value we know and whose final value on Earth we can infer. In the case of a supernova, an adequate standard candle can be the early neutrino rates. That is, the neutrino rates emitted during the first tenths of milliseconds after the beginning of the explosion, after the beginning of the shockwave propagation. In the case of electron neutrinos at the emission point, you can see here that the size of the emission peak, initial emission peak corresponding to shockwave propagation, is extremely stable with respect to changes in the progenitor, supernova progenitor properties, and changes in the features of the simulation, the way it is modeled. In general, we don't have access to this peak. For example, in water Cherenkov detectors, we have antineutrinos, but we could still measure the number of neutrinos emitted during the first 50 milliseconds of the explosion and get a relatively stable estimate of the supernova distance. And recently, a study by Zegerlund et al. In 2021 has shown that if you supplement this rate in the first 50 milliseconds by an observable called F delta that includes the neutrino rates in 100 to 150 millisecond window, you could get an estimate of the supernova distance down to a few % of precision for a supernova in the galaxy. This is extremely encouraging. However, these distance measurement algorithms assume that you know the neutrino properties and that you are sure that they are described by the standard model. And this is not necessarily the case. So to understand why, let's track a neutrino from its emission point down to its detection in, for example, Hyperkamiokande here, water Cherenkov detector. So first, even in the standard model, neutrinos are going to undergo matter effect, which will change their flavor composition. So in particular, one matter effect inside the star is the Mikheyev-Smirnov-Wolfenstein effect. And even in the standard model, it means that your emitted neutrino rates will depend on the mass ordering. In the standard model, there is currently a twofold ambiguity. It can be either normal or inverted. A twofold ambiguity is not a huge problem. But in addition to this, you could have new physics effects. So here, let me focus on propagation effects with heavy neutrino mass eigenstates undergoing two-body decays into the lightest mass eigenstate plus an invisible particle. In this case, looking at the orange curve, you go from solid to dash to the dashed line. So you have an overall increase in the detected neutrino rates, which could be mistaken from seeing the supernova closer than it actually is. Conversely, in the inverted mass ordering, you could see the supernova further away than it actually is. So this could interfere, sizably interfere with your supernova distance estimates. Of course, it's totally legitimate to assume that there is no new physics when you are making measurements. Otherwise, you wouldn't know, you would have to deal with a zillion of models. But during the next 20 years, it might be possible to actually stabilize, have distance estimates which are robust against new physics effects. The reason why is that currently, the supernova detection, like the bulk of the supernova searches are taken by large-scale water Cherenkov detectors, which are sensitive mainly to electron antineutrinos. During the next 20 years, these detectors are going to be better, they're going to be bigger, but they're also going to be accompanied by liquid argon detectors, which will be sensitive to other neutrino flavors. Notably, we have Dune, sensitive to electron neutrinos, and dark matter detectors sensitive to the sum of all neutrino flavors, such as darkside 20K and a bigger version of it called Argo. And to understand the impact of these detectors, let's look again at the impact of neutrino decays on the supernova rates, but now in 3 experiments, Dune, Hyperkamiokande, and Argo. So here, the blue lines are the standard model, and the orange, green, dashed, and solid lines are 4 different neutrino decay scenarios. Here, to describe neutrino decays, I use 2 parameters. R bar, the supernova distance over the characteristic decay length, which is 0 in the standard model, and which becomes larger as more and more neutrinos decay on their way to Earth. And second parameter is zeta, which is the branching ratio to active neutrinos. So if zeta is 0, then you get only sterile neutrinos as decay products, and you can get very low observed fluxes. So here you see that in hyperkamiokande, water Cherenkov detector, you have a near degeneracy between a change in decay parameters and a change in the supernova distance. This is a bad news, but you can see that in Dune and Argo, even though you have less statistics than in hyper-K, you can have heightened sensitivity to neutrino decays due to the significant change in the shape of the rate curve, like the change in the height of the peak, notably. So if you combine the statistics of large-scale water Cherenkov detectors with the shape sensitivity of the other experiments, you could be able to measure simultaneously the supernova distance and possible presence of new physics. To formalize this, we performed a study as collaboration between different APC group and the supernova modeling group at AIM at CCSNe. And for this study, we used the same supernova models as the one used for the standard supernova distance measurement algorithms, so 149 model, 9 to 120 solar masses. We modeled detection rates using SNEWPy and SNOWGLOBES tools. And for the time windows, we first considered the same time windows as in the standard supernova distance measurements, so 0 to 50 milliseconds, 100 to 150. But we split the 0 to 50 millisecond window further to resolve the neutronization peak, the initial peak region. And then, while we have different time window, we have the neutrino event counts in these different windows, so we can perform a likelihood fit of the supernova distance. So when we perform such a likelihood fit, and in order to understand the effect of neutrino decays on distance measurements, we simulated an observation of a supernova with an 11 solar mass progenitor at different distances, with R bar equals 5 and zeta equals 1. It means in practice that most of your heavy neutrino mass eigenstates will have already decayed to active neutrinos on the way to Earth. So here I'm presenting the measured distance as a function of a true distance for the best fit and for the 90% confidence interval. The gray band is what you obtain when you assume that neutrino properties are fully described by the standard model and you don't have additional degrees of freedom. So here you can see that indeed we have a bias compared to the dashed line, which is the identity. We can mitigate this bias by introducing additional degrees of freedom in the likelihood to allow for new physics. But of course, when you do this, you mitigate this bias, but you get terrible error bands. This is not nice. However, when you combine complementary experiments like Dune and hyperkamiokande here, suddenly you not only get an accurate estimate with these additional degrees of freedom, but you also gain back most of your precision. To have a more global view of it, we performed this study for more experiments for a supernova at 10 kiloparsec. And we just looked at, let me see if I can get the mouse back. And we just looked at the size of the confidence interval. So here is the size of the confidence interval. So the position is normalized to 1 for 10 kiloparsec. The dashed rectangle is what you get when the observation is like from a standard model, neutrinos obeying standard model properties, and your likelihood assumes that neutrinos are obeying standard model properties. So this is the case where you get both maximal precision and maximal accuracy. Then the light rectangle is when you have the standard model for the observation, but you have introduced additional degrees of freedom in the likelihood. And then the dark rectangle is what you is the case that I presented before, when you have neutrino decays and you have introduced your additional degrees of freedom in the likelihood. So on the right, on the left, you have individual experiments like Dune, IceCube, hyperkamiokande, and Argo, where you see your error bars blowing up, as was seen before. And on the right, you have pairs of detectors. And you see that combining Dune with hyperkamiokande or Dune with IceCube allows you to gain back almost all your precision, like with a up to 25% difference in practice. This result was for the inverted mass ordering. Going to the normal mass ordering, we get a similar result, except that here we can get a huge precision gain, even involving the Argo experiments. So all 3 experiments can help you get back both your precision and your accuracy for the supernova distance. The important point here is the complementarity. Sorry, I don't have a measurement of time, but I'm just to conclude, I have taken you through a rather packed journey through supernova neutrino detection and characterization in current and upcoming experiments. The bottom line is that the next galactic core collapse supernova will be a once-in-a-lifetime opportunity to probe the physics of the star and the physics of the neutrinos themselves. But it requires a multi-pronged approach, and it requires including as many experiments as possible. So here we have to be creative. We have seen how to successfully integrate high-energy neutrino experiments like M3net to the supernova analysis program. And we have seen how next-generation experiments could kind of open new horizons, allowing us to simultaneously estimate the supernova distance and constrain neutrino properties. And just to finish, this kind of study also featured an important technological aspect of Chem3net, which is with optical modules with multiple photomultipliers. This study at Chem3net would not have been possible without these modules. And it represents also a testing ground for future detectors, as these modules are going to be installed, maybe in hypercamiocande and in ice cube generation too. Thank you for your attention.
Thank you very much, Sonia, for this talk. So any questions?
Thank you for the very nice talk. Just back to the last two slides, I didn't understand why the particular combination of experiments that gives the tightest constraints. Like what is so specific about these experiments? And there is no KM3net in the combination also. So why only all two experiments have been considered?
Yes. Okay. So first, maybe why there is no KM3net in the combination is the quickest one. It's because what I have presented is that KM3net can detect a supernova in the galaxy pretty much at any place in the galaxy, but it's hard for KM3net to do anything beyond this. I can show you like the what you get at. Sorry. This is what you get. For example, this is a neutrino rate curve that you expect for a 20 solar mass progenitor at 5 kiloparsec, so for a very close by supernova. And you already see that you have something very noisy. So doing shape analysis for a galactic supernova, especially when at 10 kiloparsec, is very hard with Chem3net. So here we consider the experiments that have the smallest noise level and the highest statistics. And then the next question, I think, is why these particular combinations of experiments. Well, I think this boils down to the complementarity between these experiments. They are sensitive to 3 different combinations of neutrino flavors: electron antineutrinos for water Cherenkov detectors, electron neutrinos for Dune, and the sum of all neutrino flavors for these dark matter detectors. So when you bring all of them together, you can pinpoint new physics effects which affect different neutrino flavors differently, which they very frequently do. And this is how you can break the degeneracy between a change between the presence of neutrino decays and the supernova distance estimate. Yes. Let me go back to this. Yes. So the reason is the size of the time window. Because here we are trying to count the number of photomultiplier hits that come from the same event. We don't want to have pile-up. So to avoid having several events contributing to this optical module activation, we are counting the number of activated photomultipliers within an extremely narrow window. 20 nanosecond, for the final analysis, 10 nanoseconds. And living organisms, they emit a lot of light, but they emit it at a very low rate compared to this 20 nanosecond window. It's extremely unlikely that a living organism is going to emit 2 photons within like 10 or 20 nanoseconds from each other. I think that's the idea.
Why does it help to have many detectors in this regime? Because you made the point that the value of this system is that it had many photomultipliers within the box or within the sphere.
Well, it's because if you have only one photomultiplier, if you have only one photomultiplier activated, it's much more difficult to distinguish this single heat bioluminescence from like a neutrino interaction product that activates that is going to give to emit photons at much higher rates. So you could count the number of photoelectrons deposited, but this is less precise than having actually different photomultipliers recording different heats.
Just the redundancy?
I'm not sure what you mean by redundancy. Yeah, it's a repeat. It's the fact that several photons are emitted in a short time interval.
Okay, so I have a question online. Joe, please go ahead.
Yeah, thank you for a beautiful talk. My question concerns the possibility of neutrino energy resolution from the source, because this could be a way of, distinguishing different equations of state for neutron stars, etc. So is that something that's feasible in the future?
Okay, so, well, there's first, since the study I presented involved also other experiments than ChemFreeNet, there are quite a few experiments for which you can, which have a low energy threshold. And in these experiments, you can actually measure the energy with a reasonable precision, like 10% or less. And in these experiments, reconstructing the energy spectrum is quite an important part of supernova neutrino analysis. The reason why I have insisted less on this is because in experiments like IceCube, Argo, or ChemFreeNet, this is much more difficult. So here I have an example of how this is working out at ChemFreeNet. At ChemFreeNet, the current energy reconstruction algorithm assumes that supernova neutrinos have a spectral distribution, which is described by a pinched Fermi-Dirac distribution. I can tell you more about it later. It's like it starts as Fermi-Dirac and propagation effects are pinching it. So you parameterize it using the normalization, a mean energy, and a pinching parameter alpha, so 3 parameters. And in the current analysis, they use just the multiplicity to look for a possible hardening of the spectrum. And they made a fit of the multiplicity distribution. And with this fit, they found this areas performing a chi-square fit, I think 90% confidence region on the signal scale versus the mean energy. And you can see that it varies a lot depending on what you assume for the pinching parameter alpha. So you can get an estimate of the overall, of the global spectral parameters of the neutrinos with ChemFreeNet, but it's not going to be a precise estimate, and it's definitely not going to be event by event.
Okay, thank you.
Okay, other questions?
I may have a naive question from a non-expert. What about the neutrinos that come from the other side of the Earth? How would they, in this range, be affected by crossing the Earth before getting into the detectors?
Okay, yes, thank you. That's very interesting. So I don't have plots to illustrate this. I can give you references later. People have studied this. They won't have, okay, for ChemFreeNet, this kind of matter effects in the Earth are not going to be seen. I mean, for the decay studies, they are not going to affect them because these are really small effects compared to what I have shown here. In some experiments, like I think Hyperkamiokande, maybe Juno, when it's built, when these experiments are built, I think you could pinpoint them, but I don't remember what are the distances. But yeah, this could be seen in principle. But yeah, they are negligible compared to effects for propagation inside the sun, if this was your question.
Okay, other questions? I have maybe small, there's a question here. I have a small question. In your analysis now for the distance determination, if I understood correctly, you assume you only rely on the neutrino signal. But what if you also detect electromagnetic signal or maybe gravitational wave signal? How does this enter into the analysis?
Okay, yes, so indeed, so gravitational waves are not going to be delayed. They are going to arrive around the same time as the neutrinos, but okay, this I'm not an expert there, so I'm not sure if there are distance estimates possible with gravitational waves. Maybe it could help for triangulation, but yeah, for the distance, I don't know. It really depends on whether you have a kind of a standard candle for the amplitude of the gravitational waves, and this I have no idea.
Yeah, I think the signal is pretty uncertain for the gravitational waves, but it still will be some additional information. So I was wondering if it can somehow help.
Yes, I agree. The question is whether there is a lower limit on the expected gravitational wave flux, and is there one?
Well, I guess there is some lower limit. I'm not sure how informative it is. In fact, the models vary quite a lot. But yeah, if they converge, that will be.
Yeah, because if there is a lower limit on the expected flux, you could at least say that the supernova has to be at a distance of at least this, and this could supplement the neutrino observations. But it's true that the uncertainties are, if the uncertainties are quite high, it's a bit difficult. But maybe we could look into this.
Okay. So if there are no other questions, so let's, sorry. Oh.
The experiment, which fraction of the time is it taking data?
In the case of Chem3net, I don't have a number here because the detector is still not quite stable. So it's...
But what are the expectations for the future? I mean, is it a large fraction of the time?
Oh, it's expected to be a large fraction of the time. I don't have I just don't have the exact number in my mind. But yes, 80% at least.
What is the probability to have another experiment being active at the same time in order to...
Oh, I mean, giving the... at the same time, yeah. Well, given the number of experiments that are observing core collapse supernova, that are aimed at observing core collapse supernovae, I think right now we can comfortably say there will be at least one experiment working when there is a supernova taking place. For example, the SNEWS program right now, it has 10 experiments being registered. And many of these experiments are actually quite stable. In Super Kamiokande, for example, the duty cycle is extremely high because it's really supernova is among the main parts of its program. The detector is well known. So it's something like shifters have to react extremely fast if there is a data acquisition problem. I mean, I remember one time I was on shift when I was a postdoc and the data acquisition failed. And by the time I managed to reach Japan, it stayed 20 minutes like this due to a connection issue. And that was already a huge anguish. So that gives you an idea of what the stakes are.
Okay, last question, no? Okay, well, let's thank Sonia again.
Bonjour, je déconnecte, voilà.
Merci. Oui, juste savoir, vous avez montré un détecteur qui s'appelle Halo.
Ah oui, alors celui-là, par contre, je ne suis pas experte, hein, je sais juste